All right, everybody. So let's get started on reviewing the Robinson annulation. So let's talk a little bit about what is going on here in the Robinson annulation. We went over some practice in class, so we did some problems and we'll continue doing some problems in class, but I wanted to kind of talk about the reasons why we may want to do some things, and then we'll go through how to do it. All right, so the Robinson annulation, remember, is two steps. The Michael addition, which we've done and practiced in class, and you had your videos on that. And then the aldol condensation, and you're going to get your product from the Michael addition attacking the molecule itself and closing up in a ring, and that's why we call it annulation, because one meaning of annulation is to close inside of a ring. So we are going to draw this and we're going to practice this. So we're going to do a practice problem, and we did one in class, and we're going to continue doing practice like I said. But what I want to emphasize in this lecture is that we need to use weaker nucleophiles for the Michael addition, like enamines, like Gilman's, or we might use doubly stabilized carbonyls. And we can use these to attack the beta position. So remember, in class, we practiced some problems, and in our previous lecture, we talked about this, that we use these weaker nucleophiles because the stronger ones are going to attack the carbonyl itself rather than the beta position on the alpha-beta unsaturated carbonyl. So we're going to go through the mechanism again, but let's talk a little bit about some applications of these. So we've been talking about applications in class many times. We have our molecule of the week every week. Sometimes we have our green chemistry application. So let's talk a little bit about some of these. One application for this is that we can make a lot of these molecules that are multiple rings, and as you can see in some of the applications that we've talked about so far, a lot of them had rings, and a lot of molecules in nature have rings. A lot of pharmaceuticals have rings. If we talk about new materials for plastics and things like that, a lot of our polymers are in rings, and so it's very important that we learn how to effectively make a ring. Another application of the Robinson annulation is the atom economy. Since we're primarily, unless we add something to the mechanism, since we're primarily using the same atoms to attack each other, our atom economy is fairly high. Now, here is where it could lower because of the choice of our starting material. So for example, if we start with a ketone, not a double ketone like a dione, but if we had something that would be like a cyclohexanone, well then it is going to need to be converted to something weaker like an enamine. And if we convert to an enamine, now we're adding another step. Now it's not that bad because the enamines are fairly easy and fairly simple, but it is something that's going to add what we call add auxiliaries or add extra protection groups or add extra materials into our reaction that also lowers our atom economy. It will also lower yield. For every reaction you do, it lowers the yield. So let's jump back into going over the mechanism. Let's draw the mechanism, but what I want to do is focus on something that we practiced in class, but I want to revisit, is that when we do the Robinson annulation, we want to use these weaker nucleophiles to attack at the beta position on the alpha-beta unsaturated carbonyls. And if we just use a regular ketone, we're going to end up with a side reaction where if we deprotonate at the alpha position, now we've formed a nucleophile that then can just do an aldol condensation with itself or with another carbonyl. So let us therefore do a conversion with this, so we can do a reaction that we've practiced already and you saw in your videos. We can do a reaction with a amine And so we can convert this to an enamine. So to make an enamine, remember we want a secondary amine. And in that mechanism, we also need catalytic acid. So let's go ahead and draw this mechanism. So first, what I'm doing is making an enamine. And our enamine will help us to make a weaker carbonyl. So I'm putting carbonyl in brackets because it's not a carbonyl, but it's essentially masking a carbonyl. And remember, there could be multiple ways in which we do this mechanism. So I'm going to draw it one way, but we've talked about a couple of different steps that are also likely and possible. So one way that you guys may draw it, it's not going to happen just because of orbital overlap. Not going to happen as often, but in mechanistically, it's not incorrect. It's just orbital overlap wise, having your intramolecular proton transfer can still work, but I'm going to do it a little bit the longer way, which might be a little bit more comfortable for some students. So I'm going to shuffle this proton around. And remember, these are equilibrium steps, which is very important for us because we're going to reverse them later on. So we deprotonate this nitrogen because we want to make that nitrogen stay, but we're going to protonate. We're going to take that hydrogen. So again, we just kind of shuffled it around. We just made H3O plus, kind of just shuffled it around. And made our H3O plus, which is our acid, to protonate. All right, so why are we doing that? So we're doing this so that we'll eventually make that oxygen a leaving group, but it's not going to leave negative. It's not even going to leave while it's an OH. It's going to leave when we protonate it again. So remember, this is a catalytic solution, so we will still have some acid. It's a little bit acidic in that flask, usually around a pH of 3 to 5. Let's draw in our lone pairs. Okay. And a couple of reminders, please don't use the negative charges to attack because they're not attacking anything. It's the lone pairs that are attacking. And don't point arrows towards plus charges because the plus charges are imaginary things. Okay. Now we have a very good leaving group, and you can draw this one of two ways. You can either draw the enamine, the nitrogen kicking out the leaving group, or if you wanted to, you could go ahead and draw this where the water leaves first and then the leaving group, the nitrogen comes in. Either which way, again, there's an overlap issue with orbitals that might affect which one happens more likely, but mechanistically, we are okay if you drew it that way. So we are going to get our iminium ion, which will then later on we'll be able to convert it back to the carbonyl because we're going to reverse all these steps, so the water will come back in and do all of that. Now what's going to happen is if we were to draw the resonance structure, we'll see that this carbon is positive, and because of that we can have an elimination. So any extra nitrogen we have, because as we now know, nitrogens are pretty decent bases, especially when they're alkylated, as this one is. We're going to end up with an elimination, and we get our enamine. Now, I'm just using R for now, but you might have ethyls, methyls, propyls, whatever it is. So just be aware of that whenever you have to draw these mechanisms. And again, they're all equilibrium steps. So if I skip an equilibrium arrow, it's not intentional. Now, when we do the Michael addition, we are going to attack at the beta position of my carbonyl, and we're going to attack from the weak Michael donor that we have. So this Michael donor, this carbon has a full octet, so it has to break. What I'm going to do is go ahead and label things with numbers because I'm going to describe them that way, especially when we're joining. I would strongly recommend adding numbers to things to help us when we draw our mechanisms. So this will come over, come up. We break that pi bond. Now I'm also going to label this 7 and 6. So carbon 7 here, carbon 6. 6 is going to be now attached to carbon number 2. Carbon 2 is attached to 3. We move that pi bond between 3 and 4. So there's a pi bond there. We also had our carbonyl open up on carbon 4. So this was carbon 5, and we are missing carbon number 1, so this is carbon number 1. Now, our next thing that's going to happen is that we are going to protonate and then tautomerize. And we can draw our tautomerization a couple of different ways. So we can draw the resonance form of this to stabilize this, to make it the iminium ion back again, or we can leave it the way that it is for the next step, either which one that you want to do. This one is a little bit more stable because everybody has all its octet. So let's redraw everybody. So one thing that has to happen here, one of our last steps is a protonation step. So we have acid in this reaction. So this ends up being protonated, and now we can do our tautomerization. We can either do an intramolecular tautomerization if you want, if that's more comfortable to you, or we can shuffle around our hydrogen. So in class we've done it the intramolecular way. I'm going to draw it the other way because again, a lot of these can be done different ways, and you can choose whatever is more comfortable for you. And then I'm going to take care of the iminium ion in a bit, but I usually do it all in one step, but I'm going to come back and show you the other side after I've done this part. So if I pick up a hydrogen, the hydrogen is going to go to carbon 3. And then we can easily deprotonate this. Now I'm going to take care of the iminium side because both things are going to happen in our reaction. You can draw them out separately, but from a mechanistic standpoint, it's okay if you draw them out together. So we've drawn this before. Water can come in, open the iminium ion up. Because what we want to do now is replace the iminium ion with OH so that we can eventually form our carbonyl. All right. So like I said, I'm going to kind of go back and forth, and you can draw them separately, but just for time's sake and space sake, I'm going to draw them all kind of at the same time on both sides of our molecule. So we need to get rid of the hydrogen on our water because otherwise it's just going to go backwards and leave. So to prevent it from going backwards, what I'm going to do is take another molecule of water, or we can take our amine if there's any left over, but more than likely it's water. Deprotonate. And then, and you notice that I'm talking through it, not just for your own sake, for learning purposes. I'm talking through it because it kind of helps me follow along. I strongly recommend, as I've told you guys multiple times in class, multiple times in videos, you're not crazy. It's okay to talk to yourself while you're doing mechanisms. Just don't talk out loud in the test. That's all. But you can talk yourself through it. You can even write notes. That will help you. But the more you practice, the better you'll get at this. So I want the nitrogen to leave. So I need to protonate it. So I'm going to go ahead and I'm going to protonate the nitrogen to get it to leave. Remember, what we do in these mechanisms, many things can happen, but the thing that ideally we are going to draw, so we're not drawing everything, but we're drawing the parts that lead us to the product. So other things happen, like the hydrogens go back on the oxygen, but that never leads us to our product. And so in that case, that just reverses the equilibrium. And in that case, we just end up where we were to begin with, and it will just keep going forward until we eventually go all the way forward. Okay, now the nitrogen is a decent leaving group, so can leave. Now you can do this in one step or in 2 steps like I did here. It's up to you. Mechanistically, it's not wrong. Orbital wise, it might not be so right, but I'm only really concerned about your mechanism right now. All right, so our last step then has to be deprotonation. Now we're going to do the aldol condensation. So when you look at these problems, when you see me draw them, the next step is that we take base to our solution, and I'm going to number everything again so that we can follow along. 1, 2, 3, 4, 5. And then I had numbered this 7 and 6. We're going to do an aldol condensation, but remember, the aim is for the more stable ring. So whatever hydrogen you remove to do this process, we want to have the most stable ring. So if I were to do this, remember there are lots of different alpha positions, and remove the hydrogen here, that means the ring size that I'm going to form is 1, 2, 3, 4. That's not going to happen to close that ring up. But I could potentially, this is a very easy hydrogen, and we have one other hydrogen that we could try, but this is an easy one to deprotonate. And now we can do our aldol. And remember, the driving force, which is the question that keeps coming up over and over, the driving force for this aldol is not going to be the aldol product, but the aldol condensation product. And we did some calculations when we did this. And remember, you can do it under acid or you can do it under base. I'm doing it in this case under basic conditions. But our calculations showed us from our Spartan that the conjugated species is the most stable. Now, before I keep drawing, I'm going to number again. 7, 6, 1, 2, 3. Sorry. I'm going to renumber. And what I want to do is number, because I'm going to show you how I would draw this, because that's always a common question. Like, how do you begin drawing it? It's easier for me to draw the rings first and then to do the process of filling and everything, and that's why I like to number things. So I'm going to be attaching 5 to 7, and it's going to give me a 1, 2, 3, 4, 5 6-membered ring. So that means this side of my cyclohexane should have a 6-membered ring attached. So if this is 7 and 6, that means my alkoxide that I formed, remember these all form, these acyl nucleophilic additions form the tetrahedral alkoxide intermediate. Number 5 is joining to number 7, so that's number 5. Then number 4 is attached to number 5. Number 4 had my carbonyl. Then number 3, and then number 2 had number 1 attached to it. So our next step, we're going to protonate our alkoxide, and again, this is not a very favorable, it works, it's not, the equilibrium is not extremely favorable, but again, what drives our process is what's going to happen next. So we're going to do an elimination. So it's an E, basically like an E2 that we learned in the first semester. And the driving force, because OHs are not good leaving groups, is that alpha beta unsaturated carbonyl. Now I can do all sorts of other things with this alpha beta unsaturated carbonyl as we learned before, but that's kind of what's going on. All right,